Okay. Okay. Am I audible? Please reply me. Rajwal or any other person.
Yes,
Yes,
sir.
sir. Yes, sir. Audible.
Okay. Okay. Now I will start this. From last few lectures, we are seeing the or we are discussing about iron and iron carbide equilibrium diagram. In last lecture, we have discussed about different phases which are existing in this equilibrium diagram. In that, we have seen ferrite, austenite, then delta ferrite, and cementite. Last two phases that I have not explained in the previous lecture, that I will explain in this lecture. I will start with that, and after that, we will see the critical temperature lines. And after finishing that critical temperature lines, we will move towards the which are the three transformation reactions which are present in this equilibrium diagram. Okay, we will see one by one, and I will repeat some part from the previous lecture also. That is, what is the meaning of ferrite, austenite, delta ferrite, and cementite. Then we will start. The first phase is the ferrite. Now, what is the meaning of the ferrite? Ferrite is denoted by this letter in this diagram. It is denoted by the letter alpha or symbol alpha. Now, what is this ferrite? Ferrite is an interstitial solid solution of carbon with iron, and that iron will be in BCC crystal structure form, that will be termed as BCC alpha ion. And this ferrite is interstitial solid solution at lower temperature. Okay, I will then highlight here in this diagram this alpha. This is the interstitial solid solution of carbon uh, with iron, and that iron will be having BCC crystal structure, and that iron is nothing but your alpha ion. And this so interstitial solid solution will be present at the lower temperatures. This will be highlighted at the lower temperatures. Okay, this is the ferrite. Now, from where this word ferrite is derived, in the Latin, for iron, ferrum word is used, and from that ferrum word, this ferrite word has been derived. Now, in this ferrite, it will be very soft, malleable, and ductile phase. This alpha, it is nothing but ferrite. This will be soft, malleable, and ductile phase. And now, regarding the solubility of carbon in this ferrite, at room temperatures, here I am highlighting this point. Room temperature solubility of the carbon in the ferrite is 0.008, and as temperature goes on increasing, this solubility will also increase. And at higher temperature ranges, that is at 727 degrees Celsius, at this 727 degrees Celsius temperature, solubility of carbon in the ferrite is 0.025%. Okay, then now, regarding this ferrite, it will be ferromagnetic in nature. Generally, it is ferromagnetic in nature, but at higher temperature ranges, at this particular point, okay, at 768 degrees Celsius temperature, this ferrite will lose its magnetic properties and it will become non-magnetic in nature. Above this 768 degrees Celsius, this ferrite will be non-magnetic in nature, and below that, it will be magnetic in nature. Now, below that, it will be denoted by alpha only. And here also, we are going to denote by same symbol, but in the older days, the phase which is existing in this temperature range, 768 to 910 degrees Celsius, it is denoted. In the older days, they are using the beta symbol to denote this phase. Uh, to denote this phase. Then after that, the next phase is the austenite phase. Austenite, it is denoted by the symbol gamma in this diagram. What is this austenite? Now, this austenite is nothing but, again, this is interstitial solid solution of carbon in the iron. But here, this interstitial solid solution will be present at the higher temperature ranges, that is above this 727 degrees Celsius. And here, that iron will present in the FCC crystal structure, and it is termed as gamma iron. That's why it is denoted by symbol gamma here. And this will be, and this name, austenite name, is given in the honor of Sir, that is, he is scientist, Sir Austin. He first invented or first studied this austenite phase, That's why this phase is termed as the austenite. Actually, it is gamma phase or interstitial solid solution of carbon with gamma ion at the higher temperature ranges. Again, this gamma, or you can say that this austenite will be soft, malleable, and ductile phase. Its properties will be very much similar to the ferrite, but only one difference will be here. That is, it will be non-magnetic in nature. And after this austenite, the next phase is the delta ferrite, and this is denoted by letter delta. It will be present at the higher temperature ranges. Here you can see this delta phase is here. This is the delta ferrite. Now, what is this delta ferrite? Again, this delta ferrite will be interstitial solid solution of carbon with the iron, but this interstitial solid solution is present at the very higher temperature ranges, that is above 1400 degrees Celsius. And here carbon is forming the interstitial solid solution with delta iron. That's why this will be known as the delta ferrite. Okay, so this is the third phase. In this way, ferrite, austenite, and delta ferrite, these three phases we have learned. Then after that, next phase is the cementite. Then what is the meaning of cementite? Here, all these ferrite, austenite, and delta ferrite, these are solid solutions, or you can say that in that solid solution, these all these three are interstitial solid solutions of iron and carbon. Carbon will form interstitial solid solution with iron at different temperatures, and depending on the different crystal structure of the iron, these different names are we will get the different interstitial solid solutions. Then this cementite is the it is intermetallic compound. It is compound of iron and carbon. It is denoted by chemical formula Fe3C. This will be termed as cementite, or you can name it as simply carbide, or it is also known as iron carbide. And this cementite will be having orthorhombic crystal structure. Its crystal structure is different orthorhombic crystal structure with 12 iron atoms and 4 carbon atoms, and it will be very hard in nature, hard and brittle in nature. For your reference, if you want to see the microstructure, crystal structure of this cementite, you can see in this diagram the nature of the orthorhombic crystal structure is shown at the left corner, and at the right corner, exact crystal structure for the cementite, which is showing 12 iron atoms and 4 carbon atoms here. Iron atoms are shown by that green color, and carbon atoms are shown in the yellow color that you can see in this diagram at the right corner. And at the left hand corner, the basic format or basic of that crystal structure form I have shown here in this orthorhombic. All three axes will be unequal in length. Okay, you can clearly see that all three axes here will be unequal in length, but they will be perpendicular to each other. Okay, this is the crystal structure for the cementite. If you want for your reference, you can draw this, or I will provide. I will share these slides through emails. Okay, no problem in this. Now I will move forward. This part, up to this part, we have already discussed this in the previous lecture. Just for your information, I have repeated that part. Now after this, some mixtures are there here. Alpha plus Fe3C. Okay, alpha plus Fe3C. You can see here, this is termed as, this is the what you can say that eutectoid mixture or mixture obtained of ferrite and cementite. It will be present at the room temperatures. This will be termed as the perlite. And mixture of gamma and Fe3C, that is austenite and cementite, it will be termed as ladyburite. Okay, so these two mixtures are there, or two extra phases will be there in this diagram. And this L is nothing but the liquid solution, or you can say that liquid which is having iron and carbon both. Okay, so these are the different phases which are present in this diagram, and that we have discussed. After completing this phases discussion, now here the next part is the critical temperature lines. Okay, in this diagram, there will almost 6 critical temperature lines are there. Here I have made one separate table for that critical temperature lines. that you can draw it. But before drawing this, I will first explain what is the meaning for each line. I will start, almost six critical temperature lines are there. I will explain it one by one. Please see carefully here. Here I am highlighting this line A0. Okay, this is the line A0 line here, indicated by point A and 210 degrees Celsius temperature. Now, what is the meaning of this line? Now, this A0 line indicates the temperature at which this cementite, okay, cementite, that is the Fe3C, the cementite will lose its magnetic properties. Below that 210 degrees Celsius, that cementite will be ferromagnetic in nature, and above that 210 degrees Celsius, it will lose all its magnetic properties and it will get transformed to paramagnetic nature. And it is indicated by this dotted horizontal line shown by symbol A0. Okay, and it is also termed as the Curie temperature for the cementite. Okay, in this diagram, two Curie temperatures are there. One Curie temperature is for cementite and one for the ferrite. That I will repeat uh, after a few minutes. First, try to understand this. A0, this is Curie temperature for cementite. At this particular temperature, cementite will lose its magnetic properties and it will get transformed to non-magnetic or paramagnetic nature. Below this 210, it will be ferromagnetic in nature. Above this, it will be paramagnetic or non-magnetic in nature. Okay, this is the first critical temperature line, that is A0. And next is the A1. Okay, you can see here symbol A1. And now this A1 line indicates the temperature at which horizontal line. This horizontal line is A1 temperature line. Okay, this horizontal line DEF. Now, what this line indicates? This line indicate the temperature at which this mixture, that is the pearlite, this pearlite will get transformed to the austenite. Okay, this DEF, or you can say that eutectoid transformation line. Here eutectoid transformation takes place. This temperature will indicate that at this particular temperature, this phase is mixture of ferrite and cementite, alpha plus Fe3C. At this particular temperature, it will get transformed to austenite. Here also you are getting austenite. Here also austenite is present, and here also austenite is present. Alpha plus austenite phase is there. Means above this temperature line, whichever pearlite is there, it will get transformed to the austenite. Means this line will indicate the transformation temperature for the austenite. Okay, this is the horizontal line DEF, and it is denoted by the temperature, or this particular temperature is 727 degrees Celsius temperature. This is the A1 critical temperature line. Then after this, the next line is the A2, this dotted line. Okay, please see carefully this line which starts at temperature 768 degrees Celsius, this dotted line. Then after that, a little bit incline, and again it will become horizontal. Okay, GHEF, this is the A2 line. Now what this line indicates? This line indicates the temperature at which this ferrite will get loses its ferromagnetic nature and it will get transformed to non-magnetic nature, and it is denoted by this dotted line. When carbon percentage is 0, this this temperature is 768 degrees Celsius, and this temperature will be termed as Curie temperature for the ferrite. This ferrite will lose the magnetic property. That's why it will be termed as Curie temperature for that ferrite. Now, in this region H2E, okay, this is the carbon percentage. You can write that, that is from 0.5 to 0.8% carbon. This A2 line will be overlapping here for, above that A3 line. Okay, these two lines will coincide here in this region, having carbon percentage 0.5 to 0.8 in this region, that is HE. Okay, then after that, again this A2 line will overlap with the A1 line, and this A3 line will also overlap in this region E to F. That's why this line is the given name, or here three lines are there which are overlapping, and symbol will be like this: A3, 2 and 1. It indicates that A1, A2 and A3 critical, these all three temperature critical temperature lines will overlap in this region E to F, that is carbon percentage from zero point 0.8 to 6.67. It is denoted by A3 comma A2 comma A1. Then after this, the next critical temperature line is A3. This A3 critical temperature line indicates that, or it is indicating the temperature at which this ferrite is transforming to the austenite, A3 temperature line. And in the same way, this ACM temperature line will indicate the temperature at which this cementite is transforming to the austenite. Okay, is A3 and ACM. These are upper critical temperatures for ferrite and cementite respectively. Means A3 will be upper critical temperature for ferrite and ACM will be upper critical temperature for this cementite. Now, what this line is indicating exactly, at this particular temperature, when suppose you are heating, when temperature reaches at this point, you are having this much composition, suppose below 0.8, then that alpha which is present here, it will get transformed to austenite, means ferrite will get transformed to austenite. And if there is a cementite is present there, then that cementite will get transformed to austenite depending on the composition of that particular steel. Okay, this A3 is upper critical temperature for ferrite, ACM is upper critical temperature for cementite. Now on these lines there will be some effect of the percentage of the carbon. You can clearly see here, when carbon percentage is 0, this A3 temperature is 910 degrees Celsius. And as carbon percentage goes on increasing, this A3 temperature decreases and it will reach to 727 degrees Celsius at 0.8% carbon. Okay, I will repeat this part. These A3 ACM temperature lines are having some impact of the carbon percentage. When carbon percentage is 0, this A3 temperature is 910 degrees Celsius. And as carbon percentage goes on increasing in that particular type of the steel, then this A3 temperature will goes on decreasing and it will become 727 when carbon percentage becomes exactly zero point 0.8. And after that, whatever addition of carbon percentage takes place in that particular steel or that ferrous alloy, it is not going to affect the A3 temperature. It will remain constant after that point. Okay, after this 0.8% carbon, it will remain constant and it will overlap with the eutectoid temperature, that is 727 degrees Celsius. Now, what is the impact of the addition of the carbon on this ACM temperature? Now you can see clearly in this diagram that ACM temperature at 0.8% carbon is 727 degrees Celsius, and as carbon percentage goes on increasing, this ACM temperature also increases and it becomes 1147 degrees Celsius when carbon percentage reaches to 2%. Okay, and carbon percent reaches to 2%. So in this way, this A3, ACM or this A2 lines are having some impact of addition of the carbon in that particular material. Then the next critical temperature line is the last A4 critical temperature line. Here, this inclined line, okay, starting from the temperature 1400 degrees Celsius from point R up to point M. Okay, this line R up to M, this inclined line, it is A4 temperature line. Okay, this is the A4 temperature line. Wait 1 minute. Now you can see clearly here all the critical temperature lines, and you can see what is the significance. In the significance, just you have to write what which kind of transformation will occur at that particular temperature line. Okay, this is A0, A1, A2, A3, ACM, and A4, and their temperature ranges or the particular temperature here. For A0, you can clearly see here 210 degrees Celsius, cementite becomes paramagnetic. And A1 temperature is also known as lower critical temperature. This indicated by 727 degrees Celsius. It indicates the temperature at which perlites will get transformed to the austenite in 768 degrees Celsius. This is Curie temperature for ferrite. Again, ferrite becomes non-magnetic or paramagnetic in nature. At A0 here, cementite becomes paramagnetic. That's why it is termed as Curie temperature for cementite. And this 768 will be termed as Curie temperature of the ferrite. In E3 temperature line, that inclined line will be there 727 to 910. It will indicate the transformation of ferrite to the austenite. Then ACM, it will indicate the transformation of cementite to the austenite. Now here you can see clearly 1400 degrees Celsius to 1492 degrees Celsius. A4 temperature line is there, and it will indicate the transformation of austenite to delta ferrite. Okay, this already I have shown here. This delta, whichever austenite is present here, it will get transformed to only delta. This line is the A4 temperature line from 1400 degrees Celsius to 1492 degrees Celsius temperature. Okay, in this way almost 6 critical temperature lines are there. Please draw this table for your reference, uh, along with uh, along with the critical temperature points, their respective temperatures and their significance. I will wait for a few minutes. Please complete this, and after completion put that in the chat box that you have completed. And if you are having any query related to the phases existing and critical temperature lines, please also put that query in the chat box. Okay, I will wait for a few minutes. Please complete this diagram, sorry, this table. Okay, now we will move towards the next point. Before that, all this part I have already explained. This, what is the meaning of the ferrite and what are the properties of the ferrite phase. Then this austenite. What is the meaning of austenite? What are the properties of the austenite? And what is the what is the nature of solubility? What amount of carbon can get dissolved in this austenite as well as in this ferrite? And what are its properties? And after that, we have studied this delta ferrite phase and cementite phase and their properties also. And after that, we have discussed about this critical temperature lines. And after this, we will move forward into the actual transformation reactions which are occurring in this iron-iron carbide equilibrium diagram. Now, here I will highlight, first I will explain at which points that particular transformation is occurring, and the, after discussing that point, we will move towards the actual transformation reactions. Now, starting from this top corner, here you can clearly see this point. At this particular point, this temperature is 1492 degrees Celsius temperature, and at this particular point P, one transformation will occur. This transformation will be termed as peritectic transformation. At this point P, this is the first transformation reaction. Then at point U, the second transformation reaction will occur, and this transformation will be eutectic transformation. Then at point E, third transformation will occur, and this is the eutectoid transformation. Okay, this is the point P. It will indicate the peritectic transformation reaction. In this point U, it will indicate the eutectic transformation reaction. In this point E, it will indicate the eutectoid transformation reaction. Now, before going to see that actual transformation in this diagram, first we will try to understand what that exact during the transformation what exactly occurs. That I will explain one by one. In this peritectic transformation, what will happen? One liquid will combine with the one solid, and togetherly they will form a new solid at a particular temperature. Okay, that transformation reaction will be termed as peritectic transformation. I'll repeat it again. One liquid will combine with one solid, and they will form a new different solid that will be termed as the peritectic transformation. The next is the eutectic transformation. In this eutectic transformation, liquid will get decomposed and it will form mixture of two different solids. That is the eutectic transformation. Okay, eutectic and eutectic transformations somewhat easy to understand. That is, in the eutectic, one liquid will get decomposed to form mixture of two solids, and in the eutectic transformation, one solid will get decomposed to form mixture of two different solids. Okay, in the eutectic transformation, liquid will decompose and it will form two different solids. And in the eutectic transformation, solid will decompose and it will form mixture of two new different solids. This will be eutectic transformation. Now, we will see one by one with the percentage of the carbon and at exactly at what temperature this transformation is occurring in this iron carbon phase diagram. First transformation is the peritectic transformation, which will occur at this topmost region or topmost left corner. Now, one more significance is there for this transformation, that is peritectic transformation. Uh, this transformation will occur in the steels which are having the carbon percentage ranging from 0.1 to 0.55. If carbon percentage is less than 0.1, or if carbon percentage is more than 0.55, then this transformation does not occur in that particular type of steel. Okay, so this transformation will present in the steels which are having the carbon percentage in the region starting from 0.1 to 0.55% only. If the carbon percentage is other than this, then there will not, this phase will not, or this transformation does not occur for that particular type of the steel. Now we will see one by one. First we will discuss this peritectic transformation. Okay, this is the diagram for that peritectic transformation. Just I have drawn it separately. Okay, this is the diagram for peritectic transformation. Okay, point 1, then 0.18, and here is the 0.55. Okay, before this we will see the reactions. Okay, peritectic transformation. Here first I have shown the general transformation reaction. Already this I have explained. One liquid will combine with one solid to form a new kind of new solid, or we can say that the different new phase which will be solid in the nature. Now how this transformation reaction occur in this iron carbon phase diagram? Here you can see clearly that is delta ferrite having 0.1% carbon. It combines with liquid having 0.55% carbon at 1492 degrees Celsius, and it will produce a solid that is the austenite having 0.18% of carbon. Okay, if you are able to understand this reaction, I will show this reaction in the diagram. I will repeat it again. Uh, Delta ferrite of 0.1% carbon combines with the liquid of 0.55% carbon at 1492 degrees Celsius, and they forms or they will produce austenite of 0.18% carbon. Now, this same transformation reaction has been shown here at exactly this point P. Whichever reaction I have shown you now, that reaction will occur at this particular point P. Okay, here means delta of 0.1% carbon, liquid of 0.55% carbon combines together 0.1% delta and liquid with 0.55%, and they will produce the austenite. They will produce the austenite having 0.18% carbon. Okay, at this particular point, this peritectic transformation reaction will takes place. Okay, these reactions are shown in this diagram. Now, this depending on this transformation reaction, the steels is classified in three types at this particular point P. Okay, the steels which are having with composition 0.18% carbon, that will be termed as peritectic steel, and if steel is having composition less than this 0.18% steel, it will be termed as hypoperitectic steel. And if steel is having composition more than 0.18%, then it will be termed as hyperperitectic steel. Okay, the vertical lines shown by this number 1, it will be a peritectic steel. Then the alloy or steel shown by this vertical line 2, it is hypoperitectic steel, and alloy shown by line 3, it is hyperperitectic steel. Now, uh, this transformation will be somewhat different, which is occurring at that particular point P. For hypoperitectic steel means in this region, delta plus liquid delta plus liquid transformation will occur. The temperature range will be same, but the transformation products are different. For hypoperitectic steels, here you can see delta plus liquid, they will transform to a mixture of, again it will form excess of delta ferrite phase plus austenite will be there. Okay, austenite will remain as it is, or austenite will be formed, and excess amount of delta ferrite is formed in the hypoperitectic steels. Okay, and this same reaction will occur in the hypoperitectic steel, but there will be slight change. That is, instead of formation of extra delta ferrite, here extra liquid formation will occur. Okay, in the hypoperitectic steel, extra liquid formation will be there, and in the hypoperitectic steel, extra delta ferrite will be formed. transformation reaction will occur at the same temperature 1492 degrees Celsius. Here also temperature will be 1492 degrees Celsius. The difference is that in hypoperitectic steel, extra amount of delta ferrite will be formed, and in the hyperperitectic steel, extra amount of liquid will be formed. Okay, so this is the first transformation reaction, that is the peritectic transformation reaction. After this, I will wait for 1 minute here. Please draw this diagram. Just draw the general transformation reaction diagram on this first one. And after this, you can draw this reaction, that is delta plus liquid, and it will get transformed to austenite. And after that, you can highlight for this first reaction, you can give the name, you can give the name peritectic steel. Then write down this second reaction, delta plus liquid, it gives delta plus austenite, and delta plus liquid, it gives austenite plus liquid. Okay, total 4 reactions will be there. First reaction, this first reaction is general peritectic transformation reaction, and this is transformation reaction for peritectic steel. This is transformation reaction for hypoperitectic steel, and this is transformation reaction for hyperperitectic steel. Please write down these 4 transformation reactions. And after completing this, please put that in the chat box so that I will move towards the next transformation reaction. Please complete it fast. Okay, this is the first transformation reaction, peritectic transformation reaction. Okay, I will explain it here again. At this particular point T, peritectic transformation will occur here. Delta of 0.1% carbon combines with the liquid with 0.55% carbon, and it will produce the austenite, and this transformation will occur at 1492 degrees Celsius. And the steel which will be having this 0.8% carbon, or in which this transformation is occurring, that will be termed as peritectic steel. And the steels which are having composition carbon less than this 0.18 and more than zero point 0.1, in this region, this steel will be termed as hypoperitectic steel. And steels having carbon percentage from 0.18 to 0.55, that is in this region, it will be termed as hyperperitectic steel. In the hypoperitectic steel, extra amount of delta ferrite will be formed, and in the hyperperitectic steel, extra amount of liquid will be formed. And then after this, the next transformation is eutectoid transformation. Here I have shown general transformation reaction and exact transform eutectoid transformation, which is occurring in the iron carbon equilibrium diagram. All these diagrams I have taken from the decode garage book. You can refer that book also. Is what is the then already I have explained this. What is the eutectoid transformation? In the eutectoid transformation, one solid will get decomposed at a constant temperature, and it will form mixture of two different solids, that is S1, S2 and S3. All these are three different solids. Now, how exactly this transformation is occurring in the iron carbon equilibrium diagram? Austenite of 0.8% carbon, it will decompose at 727 degrees Celsius, and it will form mixture of ferrite having 0.025% carbon and cementite with 6.67% carbon. Okay, this mixture which is formed alpha plus cementite is termed as the perlite. Now I will explain this with the reference of the actual equilibrium diagram. Okay, at this particular point, this is the eutectoid transformation point. That is, austenite will get transformed to the mixture of ferrite plus cementite. Okay, austenite with 0.8% carbon, it will get transformed or decomposed at 727 degrees Celsius to form a mixture of alpha plus cementite. Alpha having 0.025% carbon and cementite having 6.67% carbon. Okay, this is the eutectoid transformation. Now, at this particular point, eutectoid transformation will occur. The steel will be termed as eutectoid steel. Steel having 0.8% carbon, that will be termed as eutectoid steel. And if steel is having carbon percentage less than this 0.8, it is in between this range 0.008 to zero point 0.8, it will be termed as hypoeutectoid steel. And if steel is having carbon percentage 0.8 to 2%, it will be termed as hypereutectoid steel. Okay, steel having exactly 0.8% carbon, it will be termed as eutectoid steel. And if carbon percentage is in the range 0.008 to zero point 0.8, it will be termed as hypoeutectoid steel. And if carbon percentage is in the range 0.8 to 2%, it will be termed as hypereutectoid steel. Okay, this is exactly at point E. This is eutectoid steel. If composition is less than this, it will be termed as hypoeutectoid steel. And if composition is more than this 0.8 and with less than 2% in this region, this will be hypereutectoid steel. Okay, and the third transformation, okay, you can clearly see here, somewhat I have expanded that transformation point, that is point E at 0.8% carbon. Exactly at this point, it will be eutectoid steel. If carbon percentage is less than this 0.8, means towards left hand side of this diagram, it will be hypoeutectoid steel, and towards right hand side of this diagram, it will be hypereutectoid steel. And maximum carbon percentage will be up to 2%. Then after this eutectoid transformation, okay, this is the eutectoid transformation reactions. Uh, then after this, the last transformation reaction is eutectic transformation reaction. General eutectic transformation reaction is like this, that is liquid will get decomposed at a particular constant temperature to form mixture of two new different solids. Then in this particular diagram, this transformation will occur at a temperature point 1147 degrees Celsius. The liquid of 4.3% carbon get decomposed at 1147 degrees Celsius to form austenite of 2% carbon and cementite with 6.67% carbon. Okay, liquid will get decomposed to form mixture of austenite plus cementite. Now, this mixture form austenite plus cementite togetherly, this will be termed as a lead burite. This lead burite is unstable at lower temperatures. Whenever decrease in temperature will occur, this lead burite will get transformed to the perlite. Okay, This mixture will only present at the higher temperature ranges. This mixture is gamma plus, austenite plus cementite. Okay, now I will explain this curve with reference to our phase diagram. Okay, at this point U here, at this point U, this is the eutectic transformation point. At this particular point, this liquid will get transformed. Liquid with 4.3% carbon will get transformed to mixture of two solids. It is austenite with 2% carbon and cementite with 6.67% carbon. And this mixture, it is austenite plus cementite. Austenite plus cementite is termed as lead bevrite, and this lead bevrite is stable only at higher temperatures, means above 727 degrees Celsius. Below this, it will get transformed to the perlite. Only perlite will be present below 727 degrees Celsius. Okay, in this way, in this lecture, we have discussed the iron carbide equilibrium diagram. We have discussed about the phases existing in the iron carbon diagram. Then different critical temperature lines, and after different critical temperature lines, we have discussed the main three transformation reactions, that is peritectic transformation, eutectoid transformation, and eutectic transformation. So please draw the last two transformation reactions. Just you can draw this last reaction. Gamma with 0.8% carbon at 727 degrees Celsius, it will get transformed to austenite with 0.025% carbon and cementite with 6.67% carbon. This is eutectoid transformation reaction. Please write down this reaction, and after this you have to write down the eutectic transformation reaction. Now in this way, please write down that in this way we have completed this iron carbide equilibrium diagram. From then after this lecture, in the next lecture, we will discuss the what is the effect of the addition of the different alloying elements on this diagram, how this diagram will change, how the different phase changes will occur with the addition of different alloying elements. Please draw the diagram. After completing this reaction, draw the third reaction. This is the eutectic transformation reaction, and we will stop here within few minutes. Thank you for attending this session. Okay, I will stop here, and I will also share this presentation through that study material link. Please go through that. I will stop here. Okay, thank you.